Alright, so when I got to work this morning at 5 a.m., the campus internet was down, so I sat around for a little bit, seeing if it would get better. It didn't seem to get better, so I came home around 6 a.m., and as I'm recording this around 7 in the morning, it still is broken. I can't get to Felix, I can't get to Blackboard, and apparently I can't even receive emails. So instead of meeting in class, I'm making this video so that everyone can still attend class and so on. So um, I won't make this a full 50 minutes because I don't know if people on campus, say students living in the dorms or something, even have internet, and I don't want you to have to spend a lot of your time over the weekend watching a full hour of stuff. So what I'd just like to do today is do a couple problems on concavity. Um, now I won't be able to assign, even if I finish all this stuff, I won't be able to assign homework because I can't access the server, and neither can a lot of you. In fact, nobody can, I'm sure, unless you maybe are physically on campus. And this is not fair. So probably I won't. I might finish what I need to do for the homework technically, but I won't assign it till next week because it's messed up. So all I'd like to do today is a couple examples to kind of give you something to think about over the weekend. So on the 29th, we started doing this stuff, and I talked about concavity, and it's this idea of concave up looks like a smile, concave down looks like a frown. I like to say concave down is concave frown. Oh, you can't see that. Let me see. There we go. Concave up looks like a smile, concave down looks like a frown, and concavity is determined by the second derivative. So essentially we're going to do the same stuff we were doing with the little chart with the first derivative, but we'll also consider the second derivative. Now, a place where the first derivative function meets a maximum, or a local maximum or a local minimum, is actually called an inflection point. It's a place where concavity changes. So we're going to actually have to find critical points not only of f, and that finding critical points of f means you set f prime equal to 0, but also critical points of f prime, where I'm going to have to set f double prime equal to 0. And those are going to be the points that break up my x-axis, and then from there I will calculate. So the easiest thing to do is just do an example. Okay, so example, let's find where the function, let's start with an easy one. F of x is 2x cubed plus 3x squared minus 36x. Find where this function is increasing, decreasing, any local extrema, so that would be local maximums, local minimums, its concavity, and that's the analysis of the second derivative, and any inflection points. Now, inflection points are places where the concavity changes from concave up to concave down, or vice versa, from concave down to concave up. And these points, these are extrema of f prime. So I'll find those such points by setting f prime prime, in other words, the second derivative, equal to 0. Find the critical points of f prime, and then do the same kind of analysis that I was doing in the past. So solution here, first we need to find critical points. And okay, so what will those be? Well, to do that I have to take f prime and that's the derivative of this polynomial. Well, that's easy to compute, right? That's 6x squared plus 6x, and I'm going to set that equal to 0. So I have this quadratic polynomial equal to 0. Luckily, there's no constant term because the derivative of the 36 was 0. So I can solve this by factoring out an x. Really, I can factor out a 6x, but whatever. And I'll get two solutions. I'll get x equals 0, or I'll get 6x plus 6 equals 0. Now, this thing is easy to solve. You subtract the 6, you divide by 6, you'll get x is minus 1. So these are my critical points. Those are places where f could have a maximum or a minimum. So these are critical points of f. We also need to find critical points of f prime. Now, finding critical points of f meant I took the derivative of f, and I got f prime. Finding critical points of f prime means I have to take the derivative of f prime. In other words, the second derivative. And so I'll take the derivative of this thing, and that's going to be 12x plus 6. Okay, so I got to set that equal to 0 as well. And what do we get? Well, we'll get x is minus 6 over 12, right? Or in other words, minus 1/2. So that point is a potential inflection point. So these are potential extrema of f. That's these critical points. And this is a potential inflection point. Now, whether something's an inflection point or not is the same exact analysis we've been doing with the first derivative test for testing if something's an extremum. Okay, so let's make our little chart. Now, you could argue doing all this on one horizontal axis, but what that would do is it would give you a lot more test points to make. So I recommend going ahead and just doing two possibilities. So if I want to be evaluating f prime, I need to put my critical points in at 0 and minus 1. And I need to pick my test points. Something over here might be minus 2. Something in here might be minus 1/2. Something over here, a good one, is 1. And over here I put this inflection point. And I have to pick a point to the left, maybe minus 1, and a point to the right, maybe 0. Okay. Now, I only put these here to remind myself what I'm plugging these test points into. So f prime at minus 1/2. Now, that's not such a bad polynomial, but I'll show you the general method in order to compute these, because you may end up with complicated ones in the homework or something. So I recommend using Wolfram Alpha, and I'll type in here my f prime. And then I'll just say at x equals minus 2, okay? Because this will tell me about this inflection point. Now you see I got 12. Now all I care about is the SIGN sign of that point. So I got a plus there, okay? Now my next critical point, or next test point, not my critical. I know at the critical point it's 0, right? I solved for 0. But the next test point I got a negative. And then at the next test point of 1, I ended up with positive again. So what's that tell me? That tells me that the function was increasing for a while. So f was increasing for a while, then decreasing. So I have a local max there. Then it was decreasing for a while until it started increasing to the right of 0. And then I had a minimum. So this analysis tells me local max of, and I'm going to leave a blank there for the moment, at x equals minus 1, at that critical point, okay? Critical points are where local maxes and mins occur. And we have a local min of, and I'll leave that blank again because I'll come back and fill it, of that at x equals 0. Now, what goes here? Always the value of the original function, okay? At least when you're talking about maxes and mins. So we have to plug minus 1 into the original function. Now, that's easy to do. Minus 1 cubed is negative, minus 1 squared is positive, so I get minus 2 plus 3, which is 1, minus 36 is minus 35. So here I get a minus 35, a local max of minus 35 occurring at x equals minus 1. And here I have a local min of, and then plug in x equals 0 here, and I'll get minus 36 at x equals 0. Okay, so that handles the increasing and decreasing and the maxes and mins of the function f. Now over here, I need to be plugging in the values into the second derivative function. Second derivative function is 12x plus 6. So okay, let's put that function into our thing here, and we'll evaluate it at these test points that we have. Over here it was minus, and then over at 0, well, clearly at 0, I'll get 12 times 0 is 0, so I'll get 6. That's positive. So that tells me over here it's concave, f is concave down on the interval from minus infinity to minus a half. Okay, and this is telling me that f is concave up on the interval from minus a half to infinity. Now let's plot that function f and observe this stuff as happening, right? So here's Desmos, here's the calculator, and if I plot the original function 2x cubed plus 3x squared minus 36, here's our picture. Now let's find our local max. The local max looks like it's right around here, and notice that's exactly what we saw. A local max of minus 35, which is the height of that, the second coordinate of that point, occurring at x equals minus 1, which is the x value associated with that point. The minimum's right here. It's a minimum of minus 36, the value of the minimum, and it's occurring at the x value 0. Okay, so we had that. Now what's going on with 1/2? And then this this analysis. Now, because it switched from plus to minus, we can say there's an inflection point at x equals minus half. Okay, that's the conclusion that we can make. So where's minus a half? Now minus a half, let's see, on this graph would be minus 0.5 right here, minus 0.5 and minus 35.5. So there is what we discovered as the inflection point. Now notice, to the left of this graph, the graph sort of looks like a frown face, right? It's opening up downwards. And to the right of this point, the graph's opening upwards. So we have a smile to the right, that's concave up, and to the left we have a frown, that's concave down. So that is the only place that concavity changes. So we'll never see anywhere to the right that the graph becomes, say, increasing concave up, which is possible. We saw that in the 29th of September notes. So again, back to these pictures, if you're increasing concave up, you look like this, and that's what we're observing here. Okay, that the graph is going up, so it's increasing, and it's concave up. Well, it's decreasing for a bit, and then it's concave up, and it's going up for a while. Also notice that this is telling us increasing and decreasing as well. It's saying that the function's increasing until it reaches minus 1, then from there to 0 it's decreasing, and then from to the right of that it's increasing. So all that information of the shape of this graph is encoded in that information about the derivative and the critical points and things like that. So that's a good example. Okay. So I'm going to move on to another one. And like I said, I'm only doing a couple of these today just to get you some content. I'll do more of these on Monday. Probably I'll assign a written homework, and I'll make it due next week, so there's plenty of time for the IT to get everything fixed. The next one I want to do, same instructions. And now my function that I want to look at is the function f of x is sine x plus cosine x. Okay, so some of you are feeling a little wheezy about this example because, well, we're going to have to set trig functions equal to 0 and solve them. You should have learned to do that in trig or a pre-calculus course. If not, I'll remind you. Okay, so first we got to find the critical points of f, and that means we need to find f prime, and the derivative of sine is cosine, and the derivative of cosine is minus sine, and I need to set this thing equal to 0. Now, when I do this, let me put a restriction. Let's say that x goes from 0 to 2 pi. The reason I need that is because sine and cosine are infinitely wiggly, and if I don't put such a restriction on, then this equation will have infinitely many solutions. If you took trig here, you'll remember, and I'm sure many places do this, that restriction was pretty natural when you were solving trig equations, because if not, you have infinitely many answers. So how can I do this? So it's not easy to solve such a problem, but it is possible. So we have the relationship that cosine x equals sine x. And this comes back to the unit circle. Let me do the unit circle on the computer here. Now, the sine and the cosine function, they are defined on the unit circle, not here, although there's a lot of weird trig functions on this one. They're defined on the unit circle in a way that, let me find a stupid picture first. Here it is. Here's the unit circle, and the sine of an angle is the second coordinate on that circle, and the cosine of one of these angles is the first coordinate on that graph. So what we have, our equation says, well, when is the sine of x equal to the cosine of x? Well, that's a question of for which angles are the first and second coordinates the same? Well, that would be this angle, red angle right here, and this red angle down here. So we get two answers in terms of one rotation, one round about this circle. So looking at the unit circle, there's no algebraic way to solve this, at least without complex numbers. So we'll get x is pi over 4 and x is 5 pi over 4 out of that. Now those are our critical points for our function f. Okay, so now let's find the critical points of f prime. So just like when I found the critical points of f, I had to take the derivative of f. When I find the critical points of f prime, I take the derivative of f prime, so I have to compute f double prime. Now the second derivative would be the derivative of this thing. That would give me minus sine x minus cosine x. And I'm going to set that equal to 0. Well, solving this equation gives me sine x minus sine x is equal to cosine x. In other words, I'm looking on the unit circle. For points in which the first and second coordinates are negatives of each other. Okay, so we can observe on this unit circle that it's not here, and these blue ones aren't ever it, because they always have different, so it's going to be a red one. It's going to be these two, 3 pi over 4 and 7 pi over 4. So from the unit circle we get 3 pi over 4 and 7 pi over 4. Again, you could have infinitely many answers if we allowed more than one full rotation, but we're restricting our attention to just one period of these functions. So those are our critical points. And to finish this problem up, and like I said, this is the last problem I'm doing today because it's a weird day. I'll put my critical points of f on this graph, and I'm going to put my bounds on x here just to remind myself to never exceed them. So here's pi over 4, here's 5 pi over 4, here's f double prime. All my kids are awake. Usually I'm at work. They'll be happy to see me. Here's 3 pi over 4, here's 7 pi over 4, and I got to pick test points. So maybe I pick in here test point of, I don't know, pi over 8. Sounds good. Maybe I pick pi over 2 in here as a test point, and in here, if I pick, I don't know, 6 pi over 4 as a test point, then I'll still use Wolfram Alpha to calculate these things. Right here is a 2 pi over 4. I can pick, maybe I'll pick a 4 pi over 4, that's pi. And in here, maybe I pick 8 pi over 4 is 2 pi. I don't really want to pick the endpoint. So this I'll think of as like 14 pi over 8. And so maybe I'll pick 15 pi over 8 in that spot. So all I got to do now is calculate these things. So my f prime was cosine x minus sine x, and I'm going to calculate it at x equals pi over 8. Can't really do that with the unit circle, but that's okay. We get some nasty looking result, but if we click on it and then we see that it's a positive. Okay, so we get a plus right there. At pi over 2, that one we could compute by hand. F prime at pi over 2, that's cosine of pi over 2, which the unit circle tells us is, here's pi over 2 up here. The x coordinate is 0, so we get 0 minus sine of pi over 2, which is 1. So we get minus 1 out of that. That's a minus. And then at 6 pi over 4, I don't want to do that by hand. So I'll calculate this at 6 pi over 4. When I do that, it turns out I get 1, so it goes positive again. So the function f was decreasing till it reached here, or sorry, increasing till it reached here, then it was decreasing for a while, then it was increasing again. So I ended up getting, where am I going to put my analysis? Over here, I guess. We have a local max of something at x equals pi over 4, and a local min of something at x equals 6 pi over 4. And what are these maximums? Well, we go back to our original function, sine x plus cosine x at x equals the first critical point at pi over 4. And we'll get a strict value of root 2. And at 6 pi over 4, we'll get, or sorry, 5 pi over 4, my apologies. 5 pi over 4. We'll get a value of minus root 2. Okay, so that handles the minima and maxima of f, and we'll plot it at the end and observe these things. Over here for f double prime, we again have 3 test points, and the function that we need to evaluate is the second derivative now, which is this one, minus sine x minus cosine x, and now we evaluate it at test points. So the first test point I wrote down is 2 pi over 4. That's just pi over 2, isn't it? So we'll get a negative. We'll get negative 1 out of that one. At 4 pi over 4, that's pi. We don't even need to write the stupid thing. Sine of pi. Sine of pi is the y value at this point, and you can't see the minus 1 very well, but it's minus 1, 0, so the y value here is 0. So f double prime at pi is 0 minus cosine of pi is minus 1. So that's positive 1. So I get a plus here. And then at 15 pi over 8, that I don't want to do by hand. You could do it with the half angle identity, but is it really worth it? We get, looks like it's going to be negative. Yeah, negative, some negative value. And so what this tells me is that it's concave down here, it's concave up here, and it's concave down here on this interval. And this and this, we have inflection points at 3 pi over 4 and 7 pi over 4. So the final thing I want to do is plot this function and see what it looks like. So this is sine x plus cosine x. So if I plot that function, if I plot it in Desmos, I'll get sine x plus cosine x, and oh, went the wrong way. Here it is. And we said we had a local max at pi over 4 comma root 2, pi over 4 square root 2. There it is. We had a local min at 6 pi over 4 comma negative root 2. Okay, that seems to be, sorry, it was at 5 pi over 4, not 6 pi over 4. 6 pi over 4 was my test point. So it's 5 pi over 4, so there it is. If we restrict our domain to 0 to 2 pi, okay, so those are the two critical points that we found. The concavity, you see, we had an inflection point at 3 pi over 4. Now 3 pi over 4 on this function, sine x plus cosine x at x equals 3 pi over 4. Let's see where that inflection point is. It's at 0, so 3 pi over 4 at 0. Right there's an inflection point. And the other inflection point was at 7 pi over 4. That's at this position. And that has also a value of 0, so 7 pi over 4, 0 is an inflection point. And so we see right here on this portion of the graph, we had the concave down behavior. Then between this point and the next one, we have the concave up behavior. And then to the right, it's starting to go concave down again because it's going to sort of merge into this. So that's the other example I wanted to do, and I'm going to call it quits there. See you Monday on a normal day. I will probably send out some kind of written homework, but I'll make it due well into next week. That way, if the internet's still screwed up, it's not too much of a problem. Okay? See you Monday.